Now let's talk about restricting decision tree complexity. So a fully grown decision tree that we build with the algorithm that we just talked about runs the risk of overfitting. So here's a little example to kind of think about the issue here. So imagine we have a petri dish that's our data. And the decision tree is a fungus that we put into that petri dish. Now it's going to grow and expand to cover every crack and crevice of that petri dish. And we're going to end up with a picture that looks like the picture here on the left, right? Where we've got these islands of green in a sea of orange, right? And we end up with trees that are very, very complex. So what can we do to try and avoid overfitting? Well, you might think, could we just add a regularization term? You know, that's an idea that we use in linear models. But we can't just sum the betas here, or, you know, and there's no global function that we're trying to minimize, right? So unlike least squares or gradient descent, where we're writing that gradient down to the minimum, there's nothing to be minimized here from a global standpoint. And there's no nice closed form solution either, right? This is a greedy algorithm. And, you know, if you've taken CS170, then you know what that is. But just in brief, we're building our tree node by node, making decisions as we go to pick the best approach at each node, right? So there's no place to put a regularization term. So what can we do to restrict the growth? Well, let's look at two approaches that could help us limit the growth. So the first approach is we're going to set one or more special rules to prevent the growth. So some of the examples might be, we won't split a node if that node has less than 1% of the samples. Another example of a rule is we won't allow nodes to be more than 7 levels deep in the tree. Right? So these are two examples of how we could limit how much we grow the tree. The other approach is to prune. So we're going to allow the tree to fully grow, and then we're going to explore the tree and see, are there rules that affect very few points, right? And so as an example, here we have a subtree that's circled in red that covers 40 samples, right? But if we drill down into that, we could find smaller subtrees that might only cover a few points, right? And so one way to prune is to look at one of these subtrees. So here's a subtree that starts with class Virginica, right? And contains nodes from Versicolor and Virginica. So what we can do is take our original data set, split it into 3 sets: our training data, our test data, and a validation set. And then we build our build our decision tree using our training data and tune it using our test data. And once we're happy with it, we prune it using our validation data. And so we look at a node and see what happens if we replace it by its most common prediction. So here, the most common prediction would be Virginica for that top purple node. So we say, instead of that entire tree, that subtree, we're just going to replace it with Virginica. And then we look at our validation accuracy and see what the impact is. If there's no change to our validation accuracy, then we don't need that subtree. The decision tree is general enough. And we're not gaining anything other than complexity and the risk of overfitting by including that subtree. So 2 different approaches that I just covered really briefly. I don't want to really go into them in any further detail. We're not going to have any quick checks or anything else like that on it, because really what we want to focus on is a much more elegant approach, which is random forests. And it's much more popular. My students use it in their research. I use it in my research. And it's a really nice, elegant approach. So with that, let's look at random forests. So random forests, here are 2 different subsets that I've taken from the data: a subset A that I've sampled from my data, and a subset B that I've sampled from my data. And I build decision trees. So as we've seen, when we build a fully grown decision tree, it's almost certainly going to overfit the data. We end up with these islands that are just for a particular point that was in the training data that's not necessarily representative of what we'll see when we look at a broader data set. And so we end up with models that have very low model bias, right? So that's good because that means they capture everything, all the intricate, complex details of the data. We see those islands. But they also have high model variance, which means that if I just make a small change in the data set, I could end up with a very different decision tree, right? And so if we look at the two models on the right, which were trained on different subsets of the same data, we can see that yes, at a course level, there are a lot of similarities. But then we can also see that there are some significant differences between the decision trees that result. So the approach we're going to use is random forests. And here's a little bit of the intuition behind it. Let's say I show you a cow. And I ask you, how much does that cow weigh? How accurate do you think you're going to be able to tell me the weight of that cow? Now, if you grew up on a farm, you'll probably give me a very accurate number. But if you didn't, you're going to take a guess. And that guess might be wildly wrong. You might be off by orders of magnitude. But now, if I ask that same question of everybody in the class, I'm going to get guesses all over the place. If I take the average of those guesses, I'll end up with something that is actually quite accurate in approximating the weight of that cow. This is called the wisdom of the crowds. And that's the approach we're going to use here. The idea is we're going to build many decision trees and have those decision trees vote. So here we have 9 different decision trees that we've built from our data. So what do we mean when we say vote? Well, what I mean is that for a given X and Y, so our 2 different features here, whatever prediction is most popular. Right? So let's look at the example in a little bit more detail. So that point that's highlighted in each of these graphs of the 9 is the point we want to predict. Well, in the first row at the top, we can see that all the models predicted to be orange. So that's 3 votes for orange. The second row, we have 2 votes for orange and 1 vote for green. So now we're at 5 for orange and 1 for green. In the bottom row, we see 2 additional votes for green and 1 vote for orange. So we end up with 6 total votes for orange, 3 total votes for green. So the random forest prediction here will be orange. Okay, so immediately you should have a lot of questions. And the first question you should have is that, well, we only have 1 training set. So how do I build these 9 different trees using 1 training set? Well, there are 3 different approaches you might consider. The first, and what I actually did, was just simply to take different subsets, 9 different subsets of the 150 samples. Second approach would be perhaps to take 1 sample and introduce some random noise to create 9 different samples. The third approach is called bootstrapping. And bootstrapping, and we're going to use bootstrapping or it relies on bootstrapping, and it's called bagging. So bagging is short for bootstrap aggregating. And here's the idea. We're going to generate bootstrap resamples of our training data. So we're drawing samples with replacement, and we're going to fit 1 model for each resample. And our final model is going to equal the average predictions of each of those small models. So this approach was invented right here at Berkeley in the statistics department by Leo Bremen in 1994. So we end up with these 9 different models in this example. But using bagging alone oftentimes is not going to be enough to reduce model variance, right? And why is that? Well, that's because the decision trees are often going to look very similar to each other, right? And that's because there's often 1 strong feature that's always used for the first split, right? So you can see here all of the different models have like this, for as an example, the upper blue left corner. The blue in the upper left corner, rather. So because these decision trees look very similar to each other, they're going to make similar predictions, right? And so the ensemble is still going to be a model that has low bias, but high model variance, right? Because there's this one strong feature that we use for the first split. And there might be a small number of features that are used for the second split, and so on. So these trees are going to look very similar. So instead of saying, I'm going to look at all the features and pick the strongest feature, the approach we're going to use is to use a sample of M features at each split. Okay, now usually M is equal to something like, for example, the square root of P, where P is the number of features. So if I have 4 features, at any given point, I'm only going to look at 2 of those features chosen at random to make my greedy decision. So now the algorithm is going to create individual trees that are each going to overfit their data, but in a different way. Because at each step, they're using a different random subset of those features. So the hope is we end up with the wisdom of the crowds, and the overall forest has low variance in it. Okay, so let's go over what our algorithm will look like. So we're going to bootstrap the training data t times. And for each of the resamples, we're going to fit a decision tree by doing the following steps. We start with the data in one node, and we're going to proceed until all of the nodes are pure. And we're going to pick an impure node, and we're going to pick a random subset M features. And from that subset of M features, we're going to pick the best feature X and split value beta. Again, with the goal of minimizing the loss function of the resulting split. So our weighted entropy function. So an example would be we pick the feature petal width and a beta of 0.8. And then we'll split the data into 2 nodes, where one is that feature X less than beta, and the other is that feature X greater than or equal to beta. And now when we want to predict, we'll just ask all t decision trees that we created for their prediction, and then just take the majority. So the hyperparameters here are going to be t, the number of bootstrap training data times, and m, which is the size of the subset of features that we're going to pick at each of our steps. So 2 key concepts here. One is that we're doing this bootstrap training, and the second is that we're picking a random subset of M features. So we've seen lots of different approaches, or several different approaches, to avoiding overfitting of decision trees. We can prevent the growth, or we can try pruning, or we can use something like random forests. All of these are really heuristics, right? We cannot prove that they will yield the best result, right? Or that they're mathematically optimal. And so instead they're just, somebody was experimenting and said, what if I did this? What do I get? I get something that actually gives me good approximations of what might be the optimal choice. And so they work well. Now, why do we want to use random forests? Well, random forests as a tool are very versatile. We can do both regression and classification. So we saw classification, and in just a moment, I'm going to show you how we can use them in regression. They're invariant to scaling our data or translating it in space. They also effectively automatically select the features that we want to use. The greedy algorithm is going to look and pick the features that have the biggest impact. We end up with nonlinear decision boundaries without having to do something really complicated in terms of trying to engineer our features, right? The nonlinear decision boundaries just fall out of the iterative construction of our decision trees. And with something like random forests, the expectation is that it's not going to overfit as often as other types of nonlinear model-based approaches, like ones using polynomial features. So this is an example of an ensemble model, right? We combine the knowledge of multiple simple models to make a sophisticated model that's accurate. So this is also an example of using Bootstrap to reduce the model variance.